This video briefly describes some of the design elements used in the project. First, we'll talk about the mechanical design elements shown basically at the top of the screen here, and then we'll go into a little bit of the electronic design. This first item is a two-bladed turbine that snaps onto the flywheel of the Stirling engine. It has dovetail features on the rim to allow it to be clamped on with a little clamp. The dovetails are symmetrical to keep the turbine balanced. The purpose of the turbine was to push air and make the flywheel generate enough thrust to have the whole Stirling engine rotate on a turntable. However, two blades were not enough. The next item is a little dovetail clip used to secure the turbine to the flywheel. These clips are a tight fit and they have no tendency to slip. There's an extra clip opposite the clamping clip just to balance out the turbine. Since the two-bladed turbine didn't provide enough thrust, I designed one with 6 blades to see how that would work. It has the same dovetail principle as the previous two-bladed design. The dovetail portions actually get in the way of adding more blades. This version almost provided enough thrust to keep the whole Stirling engine rotating on the turntable. I had to go back to the drawing boards and create a 12-bladed turbine to see if I could get some more thrust out of it. There's not a lot of room for a larger turbine, and even on this design you can see some notches in the blades which are there to allow the pistons to operate in that space. This design just has a tiny little slot in the rims so that it can be slid over the connecting rods and onto the flywheel. Next up is an arm that I built to house a fan so that it could provide thrust to turn the Stirling engine on the turntable. And this fan would be driven by the generator that the Stirling engine is running. So still self-contained, but this time electrically driven. It didn't have quite enough thrust either. This is another flywheel attachment. It has 2 pockets for weights at either side to add mass to the flywheel. The extra mass was to see if the heavier flywheel would smooth out the vibration in the whole Stirling engine. This helped, but I thought that adding a lot more mass might reduce the lifespan of the engine. The masses that I added were actually little LED persistence of vision modules, which can create visual patterns using persistence of vision as the flywheel rotates. This design element is just a little speaker cone. It was designed to turn the little surface audio driver into a speaker. The driver element just attaches to the small flat surface at the bottom. It turns out that the cone is a little wobbly and it has all kinds of its own resonant frequencies. So it made a pretty poor speaker in the end. This next item is the chassis to hold the electronics module, and a lot of excess sensor cable. On this side is a port for the vibration sensor connector. On this side is a port for the power connector that feeds the electronics module. And on the other side over here we have 3 ports for the thermocouples. On the end we have a port for all the cables that go out to the Stirling engine. The square holes in the bottom are just to save plastic, but cables can also be run through them. Internally we have a forest of posts which allow us to wind up the excess sensor cable and store it below the electronics module. The electronics module just snaps in place above all the cabling. The top of the electronics module is left open so we can access the switches and see the LED and so on. I've also designed a little stand that clips into the holes on the bottom to allow the display to be tilted up. This is the chassis stand that holds the display at a viewable angle. The two clips at the top of the stand just clip into holes in the bottom of the chassis. The hole in the top there allows cables to go into this tube and come out the front towards the Stirling engine. There's also room in the tube for the power conditioning circuit board. At the front we have an opening that allows the power cable to come up to the electronics module and allows access to the USB port to power it from USB power. This little stand helps to keep all the wiring neatly tucked away. In this orientation, the Stirling engine would be off to the right where all the cables come out, and the module would be on this inclined plane where the clips are. This next item is the chassis for the electronics module that has the circuitry for all the sensors. The square holes in the bottom are just to save a little plastic. This end has a hole for the power connector. This hole is for the vibration sensor connector. And there are 3 holes for the thermocouples on the other side. All the cables come out the top and go towards the Stirling engine. All of the excess sensor cable just gets stored underneath the module. Next we'll talk a little bit about the circuitry. This circuit just takes the power from the generator and feeds it through a bridge rectifier and a filtering capacitor. This is needed because the Stirling engine can run in either direction and generate reverse voltages. This circuit is an amplifier for the Electret microphone. It has an adjustable gain with the P2 potentiometer. This is the main sensor circuit. Over on the left we have 3 thermocouple signal conditioning chips from Maxim, and just beside that we have the display, which is an SPI LCD display. The microcontroller is in the middle. Almost all of its pins are used. Just to the right of that I've replaced the hall sensor with the vibration sensor. And in the upper right is the current monitoring circuit from Zetex. In the lower right we have a 3.3 volt regulator which can withstand at least a 10 volt input. This is needed because the generator can generate 7 or 8 volts, which exceeds the voltage rating of the regulator on the MCU module. This is what it looks like when it's running its display from the USB programming connector on the microcontroller module. When it's powered this way, the current shows 0 because the current is not going through its monitoring circuit. Note that the voltage reading has 0.4 volts added to it to account for the bridge rectifier, which is a Schottky bridge rectifier. And I measured its voltage drop at 0.4 volts. There was custom electronics in the test wiring setup, but these were the main elements.